Hello everyone, today let's look at QB85, a pretty basic binomial question. So here we have Lebron, who has a career free throw percentage of 73%, and in a particular game he shoots 7 free throws, so assuming each free throw is made independently with this probability, what is the probability that he misses every free throw? Let's do part A first. So if we let m sub I be the event that he makes free throw I, well then the probability that he makes any given free throw is 73%, and the probability that he misses any free throw, m sub I complement, is just going to be equal to 1 minus that, so 27%. So each free throw is an independent Bernoulli trial, but we're summing up 7 of them, so that makes this binomial. So the probability that he misses every single free throw is going to be the intersection from I equals 1 to 7 of m sub I complement. So that just means he misses free throw 1, 2, 3, all the way up to 7. But since we know every single free throw is independent, well then that obviously means that this is just going to be equal to the probability that he misses the first free throw times the probability that he misses the second free throw times the probability that he misses the third free throw, and etc. all the way up to 7. And we know that the probability of m sub I complement is 27%, so this is just going to be equal to 27 times itself 7 times, so 27 to the power of 7. And this is basically equal to 0.000105, something around there. Basically a 0.01% chance that he misses every free throw, so not very high. This is the answer for part A. Okay, so now for part B, what's the probability that he makes exactly 5 of his free throws? So if you let these be his free throws, this is first, second, third, all the way up to 7. Well, this right here is one possible way that he can make exactly 5 free throws, right? He has 5 makes, these green check marks, and 2 misses. This is obviously another way he can make 5 free throws, where he makes 2, 3, 4, 6, and 7, and misses 5 and 1. So what's the probability that this specific sequence happens right here? Well, the probability that he misses the first one is 27%, and then the probability that he makes the second one, these are independent, so we multiply them, it's going to be 73%, and then 73% here, 73% here, 73 and 73, so 73 to the power of 5. And then he has 2 misses, so 27 to the power of 2. So this right here would be the event that he misses the first one, so m1 complement, intersection with m2 he made it, intersection m3, intersection m4, intersection m5 complement because he missed, right? Then intersection m6 and m7 because he made both of those. However, that's not the only way that he could have made 5 free throws. For instance, he could have made it like this. So in this case down here, he would have made 5, so m5, and then he would have missed 6, so m6 complement. And then the odds of this sequence happening right here would have been 27% times 73 times 73 times 73 times 73 times 27 times 73, so exactly the same as we had it before. So every single way that we could have sequenced his makes and misses will give us the same probability, this one right here. So now how many ways are there that he could have made 5 free throws and missed 2? This is just a basic multinomial problem. We've done this a million times. We have 7 factorial total ways to permute these items, but we have 5 of them alike, and the other 2 are also alike, so we have to divide by 5 factorial, 2 factorial. Or you could have thought about it like we're choosing 5 of our positions to be makes, or you could have thought about it like we're choosing 2 of our positions to be misses. So in conclusion, there's 7 choose 5 total ways that he can make 5 free throws and miss the other 2, and for each of these ways, he has a 0.27 to the power of 2 times 0.73 to the power of 5 chance of making 5 and missing 2. Okay, now finally in part C, it's asking us what is the probability that he makes at least 6 free throws? So obviously if he's making greater than or equal to 6 of his free throws, he's either making 6 or he's making 7. So as a formula, we just know this is equal to the probability of 6 makes unioned with the event that he makes 7. Now obviously these 2 events right here are mutually exclusive because you can't simultaneously make 6 free throws and make 7 free throws, obviously. So when you do inclusion exclusion, there's going to be no term to subtract off here for the intersection. Now first, for the probability that he has 7 makes, well obviously there's only one way that he could make all 7 shots. It looks like this. And now each one of these shots is independent, so he has a 73% chance of making it, so the odds that he makes every single one is going to be 73% to the power of 7. And again, there's only one way of permuting 7 things that are the exact same, obviously. Now for 6 makes, that means he's going to miss 1, so let's replace one of these with a miss. So now the probability that this specific sequence happens right here is 73% chance he makes the first one times a 27% chance he misses the second one, and then he makes every single other one, so 5 more, so 73 to the power of 5, which is just equal to 0.73 to the power of 6 times 0.27. So this is just the probability for this specific sequence right here. So how many different sequences could we have? So again, we have 7 items right here. There's 7 factorial ways to permute them. 6 of them are the same though, so we divide by 6 factorial, divide by 1 factorial, also known as 7 choose 6 or 7 choose 1. This is just going to be equal to 7. And for every single one of these ways that he can make 6 shots, he's going to have this probability, so we multiply this by 7. So this is the probability right here of 6 makes, and this is the probability of 7 makes. So all we have to do now is just add them up. And when you add these two up, you get something around 0.3965, I'll say, so roughly a 39.65% chance that he makes either 6 or 7. So this right here is your answer for part C.